Assalamu alaikum. Welcome to lecture number 9 and 10 of communication system course. Last time we started the new topic called modulation, and we have discussed the very basic type of amplitude modulation called double sideband amplitude modulation, in which it was nothing but the multiplication of the message signal, which we call the modulating signal, with the carrier signal, which is usually of very high frequency, much higher than the highest frequency content present in the message signal. These two signals get multiplied together and give you the output, which we call the modulated signal. The modulated signal has a very unique envelope. We would like to detect the envelope at the receiver end in order to decode the modulating signal. Normally that's how it is done, provided certain requirements are met. That's one way of, by the way, detecting the signal. We will discuss envelope detection in detail in today's lecture. We have also seen that we can easily recover the message signal by multiplying the same carrier signal with the received signal y of t at the receiver end, followed by the low pass filter, and then in the end we can easily decode the message signal m of t out of it. So we have seen the time domain and frequency domain inside of the basic modulation process and demodulation process using coherent detection, in which we generate the carrier terms at the receiver end, the same carrier as in frequency and phase as that of the transmitted carrier. But like I said earlier, we can also follow the envelope of the received modulated signal to extract the original message information that was sent from the transmitter end. But for this kind of a detection, envelope detection, we usually follow certain criteria, or in other words, we would have to meet certain conditions in order for the signal to be received non-coherently, right? Because in envelope detection, we don't generate the carrier at the receiver end, which is a great luxury at the receiver end. We get away with it, because in order to generate the same frequency and phase at the receiver end, we have to use very sophisticated equipment like phase lock loop to achieve the goal. But at times we are unable to achieve the same. So as a result, we would have errors in the demodulation process if we are unable to achieve the same frequency and phase at the receiver end. So there's another technique called non-coherent detection that tracks the envelope of the received modulated signal to decode the message signal information. You can see this envelope information is exactly the same as the shape of the message signal. So in order to achieve this envelope detection, we are required to meet certain requirements from the transmitter end, which we are going to discuss in today's lecture. Right, and another important thing that we have seen last time was when you modulate the signal, the original bandwidth of your message signal becomes twice, and we call it therefore double sideband amplitude modulated signal. This portion greater than omega c is the upper sideband, and that portion behind omega c in the positive axis is the lower sideband. So the previous bandwidth was 0 till omega m, and now the bandwidth is from omega c minus omega m till omega c plus omega m. So the overall range becomes twice compared to the original range, which is 0 till omega m. Since bandwidth is the positive range of frequency distributed about omega c as per the definition of bandwidth. So if we compare the bandwidths, the baseband signal has the bandwidth equivalent to omega m, and passband has the bandwidth equivalent to 2 times omega m, right? So after modulation, usually the modulated signal becomes twice the band compared to what it was before modulation, right? That was something which we talked about in the last lecture, right? So how to compensate it, how to reduce the modulation bandwidth? We can use either single sideband modulation or vestigial sideband modulation. These are the two variants that we are going to talk about later, after 2 lectures from now. These are variants of amplitude modulation that can save bandwidth for you. So these are bandwidth efficient amplitude modulation schemes. We will talk about them later. In today's lecture, I would be discussing about non-coherent double sideband amplitude modulation. Right? Coherent or synchronous detection requires the same carrier. Like I said earlier, that if you would like to decode the signal using the same carrier, then you have to generate the same frequency and phase as that of the transmitted carrier. This is a very complex receiver that does that job for you, and this requirement is very rigid. If you are going to make the errors in the clock or any errors in the frequency or phase, then you are going to have errors in the reception. So this means if we want to have coherent detection of the amplitude modulated signal, then we have to generate the same frequency and phase and have to meet complex requirement of the receiver structure in order to make it possible, right? So this is a costly and complex solution. Nowadays the cost is not a problem, but we would like to avoid it for some applications such as broadcasting applications. We would not go for coherent detection, right? But for point to point and for let's say multi-point to point, but for multi-point to multi-point communication such as in GSM, or let's say in 3G or 4G communication, mobile communication, we still go for synchronous detection, and we generate the carrier at the receiver end. We have a very complex receiver at the receiver units. In our mobile stations, we have a very complex unit there. But like I said earlier, if we meet the requirements of non-coherent detection, we can have very low cost receivers, and yet we would be able to decode the message signals very nicely. So let's talk about non-coherent detection, and there are some limitations attached to this non-coherent detection, and where the non-coherent detection scheme can be applied for which scenario and for what applications. I have summarized it in the slide, and soon you will be able to understand these points. The main feature of non-coherent detection is that it is low cost in nature. It only requires simple envelope detectors that work on a principle of charging and discharging of a capacitor depending upon the input. We will talk about it later, right? Later in this lecture. But the point is that solution is very cost effective. So we would like to go for it, but it has certain constraints. It can't be used for all of the applications. So the feature is that we don't need to regenerate the carrier at the receiver end, which is a very big feature, and it reduces the complexity of the receiver significantly. So this means we can have simple receiver structure. However, it requires high transmitted power. Now this is one requirement that we will be talking about and proving with the help of few examples later, that yes, the non-coherent detection requires the transmitted power to be very high. So we will see this drawback that is associated with non-coherent detection requirement. With the help of example, we will prove the power efficiency of such a system. So therefore, it's not suitable for point-to-point communication such as in GSM communication or multi-point to multi-point communication. It's not suitable for that. It will be very expensive because imagine every transmitter unit um, would have very high power inefficient transmitters. So the overall system would be uh, inefficient in terms of power. So we can't waste the power. Remember, we have talked about the performance metrics, and one of the important resource and performance metric is how much power we can, save in the communication system. So we'd not like to go for such a solution that wastes the power, right? So therefore, it is only used for point to multi-point communication. That is, we can afford only one high power transmitter, such as in broadcasting application. We may have one very high power transmitter that broadcasts the messages to all the receivers, and all those receivers are low cost simple envelope detectors. They are based on simple envelope detectors. So for this particular application, and of course this is a very widely used application, such as in radios, you go for broadcasting scenario in which there is only one transmitter and several receivers, or in other words several recipients are there to decode that message signal. So we can afford one high power inefficient transmitter, but we can't afford so many high power inefficient transmitters such as required in point to point or multi-point to multi-point communication systems, right? So we will talk about the efficiency of non-coherent detection shortly, and we will mathematically do the analysis behind it, and we will prove that non-coherent detection is indeed highly power inefficient scheme, right? So what's the theory behind non-coherent amplitude modulation? It's a very simple procedure. If you see these equations there, all we do is we transmit the carrier term along with the modulated term. If you see this first equation there, this y of t is the modulated term, okay, and modulated signal, non-coherent modulated signal. If you see here, there are two terms present in this equation. One is the carrier term, a cos omega ct, and the other term is the message signal modulated onto the carrier term. So this is your double sideband amplitude modulated signal that we have studied in the last lecture, and this one is the carrier term. So effectively you are transmitting the carrier term along with the double sideband modulated signal. So if you take cos omega ct common, you end up getting this equation, second equation there. And if you see this in this equation, we are effectively shifting message signal by some amount A. In other words, we are adding some DC shift A to our message signal M of t before modulating it over the carrier term. So it's like saying giving a DC shift to the varying analog message signal M of t and modulating the result, this bracketed term, with the carrier signal, right? So that's the only difference between coherent and non-coherent modulation scheme, that you give a DC shift, right? Now the question is how much DC shift is required to be given, and why we give the DC shift in first place at all. We will answer these questions shortly, right? So in short, instead of modulating M of t directly, we modulate A plus M of t for non-coherent detection to be possible at the receiver end. If you take the inverse, if you take the Fourier transform of it, you end up getting these terms. And this one is the modulated spectrum, message signal shifted on to carrier frequencies omega c and minus omega c, and this one is the carrier frequency spectrum. You have two spikes, one at omega c and one at minus omega c. So this term in frequency domain is these two terms are extra terms, right? This one you are familiar with. We have already seen the modulated signal spectrum. So like I said, we are sending the carrier term along with the modulated signal, so that's why you see the carrier terms spectrum in the frequency domain as well, along with the modulated signal spectrum. right? Now let's figure out how much DC shift is required and why we give the DC shift in first place at all. Now imagine you have this message signal M of t. Assume this is some random message signal representation M of t, and it is assumed to be clipped from the two extremes. Say it is clipped such as it is limited by peak to peak, positive peak MP and minus MP, the negative peak, right? And assume these two peaks are the same values, MP and minus MP. So it's a very hypothetical scenario in which you have a message signal whose peaks positive, both peaks positive and negative peaks are the same. You are required to modulate it using some carrier frequency cos omega ct. Okay, some carrier term cos omega ct. For non-coherent modulation schemes, we just seen that we have to give it a DC shift, right? So here in the next figure we have two scenarios in which two different types of DC shifts have been given to this message signal M of t before we modulate it using the carrier term cos omega ct. Here the DC shift is given such that the overall message signal M of t becomes positive for all times t. You can see here the negative terms of message signal M of t are not negative anymore when you give such a DC shift A, okay, in this scenario, right? And here in the third figure there on the right, you haven't given sufficient DC shift A to the message signal M of t such that all of the message signal components become positive in amplitude axis, right? You can see here some portion of message signal still lies below the zero amplitude line. That is, some portion of the message signal is still negative, right? Is having negative values. So this means A plus M of t is not greater than 0 for all times t for this scenario, but it is true for this scenario on the left side. You can see here. Okay. So now if you separately modulate these two transformations of the message signal, you end up getting something like this here in this scenario when message signal is all positive for all times t after the transformation. You end up getting this kind of an envelope, right? But on the right hand side you can see some portion of the negative term, when it will get multiplied with the negative terms of the cosine term during the modulation process, it will become positive. In other words, some portion of the modulated term will become inverted as a result, right? And if you connect these peaks, if you construct the envelope out of it, you can see the shape of the envelope changes, right? It is not equivalent to the original envelope of the message signal, right? But here you can see if you connect the peaks, you can see you get the same message signal out of it. If you are able to detect the envelope out of this modulated signal somehow using some envelope detector circuit, you would be able to extract the approximated shape of the message signal out of this modulated signal being received. But here if you do the same process, you would be recovering slightly different envelope. And why it is different, and from what times it is different? It is different after the times when the message signal was negative in those times, right? You can see here the envelope is inverted. So here the message signal will be corrupt in nature. The envelope detection will give you the wrong output. It will have errors. Why? Because the message signal was still negative for some times t, even after giving the DC shift. But here in this scenario, the message signal becomes positive because the DC shift made it positive for all times t, right? So now you can see that if we can achieve this requirement, if we can achieve this scenario in which the message signal becomes positive for all times t. You can see the message signal in the envelope of the received modulated signal, and you can detect it using any envelope detector, right? Very easily. But here you can't do it. You have to go for other solutions, synchronous detection of the received signal. You have to generate the same carrier in frequency and phase as that of the transmitted carrier for this scenario. If you want to recover the message signal out of it, you can't recover it using envelope detection. But here, yes, you can do it using envelope detection. So this tells us about the condition over A, amplitude A, how much of the DC shift is required to be given. That depends on the message signal, the negative peak of the message signal. That is how much maximum negative value is present in my message signal. I would give the DC shift such that that negative value becomes positive for all times t, right? So in short, there is a requirement that A plus m of t should become greater than equivalent to 0 for all times t, right? But how much greater? Like you can have A indefinitely large, right? And all those A's will meet this requirement. A plus m of t will become greater than 0, right? But remember, A is nothing but the amplitude of the carrier term. Remember, we are adding this term along with the modulated signal, and this term alone is called the carrier term, right? And the amplitude A is there, which is associated with the carrier term. So if A is very large, this means your carrier term's amplitude is very large. And if you compute the power of this carrier, it will be very large, because we know the average power of this carrier is A square by 2, right? So if A is large, the carrier power is going to be very large, right? So now let's see what's the minimum value of A we can have, right? So the minimum value depends on the minimum negative value of maximum negative value of your message signal. Assume that maximum negative value is MP, right? Its absolute is MP. So A is the minimum value of A that you can have is equivalent to MP. So we define, next we define the modulation index mu that determines how much of DC shift you have given to the message signal before you modulate it. The modulation index mu is the ratio between the peak negative value of the message signal and divided by the amplitude shift, the DC shift that you are giving it to. If you select A equivalent to the maximum negative peak value, that is MP, so this mu will become equivalent to 1, right? And if that A is larger than the maximum required, right, then you will see the mu will be smaller than 1. And how large A can be? I've told you it can be indefinitely large. For example, A can be infinity. So 1 over infinity or MP over infinity will be 0. So the range of mu starts from 0 till 1. Maximum value of A can be infinity, and the minimum possible value of A can be MP. We cannot reduce the value of A below MP. What will happen? If we do that, some portion of the message signal will remain less than 0 for some times, and as a result we won't be able to use envelope detectors at the receiver end. So A cannot be less than MP. So that's why the requirement for mu in order to make the envelope detection possible is that you have mu within this range starting from 0 till 1. It is best to keep the mu near 1. Why? Because in that case your A will be equivalent to the bare minimum required, okay, equivalent to MP in the best case scenario. So if A is less than MP, you are doing over modulation, and non-coherent detection cannot be done. The mu would be greater than 1 in that case. So you would have to go for coherent detection when that is the case. But if you keep A within the limits, then you get mu within this range, and then you can do the non-coherent detection, right? So now how do you implement the transmitter side of it? In short, we are giving a DC shift to the message signal first using some adder block. Let's say you have this message signal here, and that's the DCA here. Now since you know the message signal and its amplitude that you want to send, you know the maximum negative value of the message signal as well, and accordingly you choose the value A. You give a DC shift to that message signal using some adder block, and you end up getting A plus M of t here. Then you modulate it using the carrier term cos omega ct using any multiplier block, as you did in the last lecture. In the end, you end up getting the two terms, A cos omega ct, which is the carrier term alone, and M of t times cos omega ct, which is the double sideband spectrum, which is your total. The sum of the two is the double sideband non-coherent modulated signal. That's the envelope of the double sideband non-coherent modulated signal. You can see here A plus M of t. If you track the peaks, you would be able to extract the message signal out of it. That's how the spectrum, as an example, that's how the spectrum of the double sideband amplitude modulated signal would look like on using some, let's say, frequency analyzer. This term left hand side is the spectrum of your message signal. Assume it has only one frequency present in it, and this one here is the modulated signal spectrum. You can see here the spike there having a very high power is the carrier term. In this particular scenario, 4 kilohertz carrier is being used to modulate this message signal. Message signal spectrum is such that it has only one frequency component present in it, and it's about 500 hertz, not to be exact, but around 500 hertz. So you would see the carrier you would see the carrier term there, right? That is coming out of this term here, A cos omega ct, the spectrum of the carrier term, and the other spectrum is because of this second term there, M of t cos omega ct. There, omega c plus omega m and omega c minus omega m. Omega c was, or in other words, fc plus omega fm and fc minus fm. Fc was 4 kilohertz, and when you add fc plus 500, it will become 4500 hertz in frequency domain, and fc minus 500 becomes around 3500, right? So this is your spectrum of double sideband amplitude modulated signal, non-coherent amplitude modulated signal. And remember, we are only showing the positive frequency axis, and of course you only see the physical real world frequencies which lie in the positive axis of the frequency. Now next, let's compute the power efficiency of such a modulated signal scheme. We have two terms in the modulated signal spectrum. One is the carrier term and the other one is the double sideband modulated term, and we call it sidebands in short. We would like to see how much power is there in sideband compared to the power in there in the carrier term. Because remember, the message signal lies in the sideband, and the amount of power that carries it is referred as the useful power. That's not the useful power that is associated with this term, because the message signal is not there in this term. Message signal lies here in the sideband. So the amount of power that carries it is the useful power. So we are going to compare this useful power out of this term divided by the total power, that is the power, sum of the power of the two terms. So we define an efficiency parameter, useful power divided by total power, which is nothing but equivalent to the sideband power, that is the power in this term, divided by the total power, that is the power in the sideband plus the power in the carrier term alone, right? So the carrier term doesn't contain any useful information. The carrier term's power is wasted for convenience and hence a trade-off. And I would like to know if you understand this trade-off now. Because if we would not give the DC shift, the required amount of DC shift to the message signal, we would not be able to decode using envelope detectors. And envelope detectors are very cost-effective solution of detection, right? So we have to give a DC shift, a certain amount of power is to be wasted, right? So if you want to simplify your receiver structure, go for non-coherent detection. But of course, you would be restricted to point to multi-point communication only, because you don't want to come up in a scenario in which all the mobile station units have inefficient transmitter powers, right? In that case, you don't go for non-coherent detection, you go for coherent detection, and you compromise over complexity, right? So that's how we calculate the efficiency, and with the help of an example, we would like to compute the efficiencies of a non-coherent modulated signal. After a break, we will do that for you.
A very simple example to prove कि ये power inefficient system है. You are given with a message signal जिसकी कुछ mathematical relationship है, something like that, B cos of omega mt. Your message signal is having just one frequency present in it, omega m. Your carrier signal is A cos of omega ct, where omega c is much greater than omega m. That is understood. ये modulation में ये होगा. आपका जो क्या कहते हैं म्यू की रिलेशनशिप है विद MP and A, वो आपके सामने, राइट? ये हमने पढ़ा था, म्यू मॉड्यूलेशन इंडेक्स, इंडेक्स, that is MP over A, where MP is the peak value in the negative amplitude, negative peak value of the message signal. In our case, MP would be equivalent to B, ठीक है? आपके मैसेज सिग्नल की पीक वैल्यू B है, ठीक है? नेगेटिव साइड में भी यही है, B. तो आपकी केस में ये B over A हो जाएगा, ठीक है? And A would be equivalent to B would be equivalent to mu times A. सही? जी.
सर हम हमेशा जो DC शिफ्ट होगी हमें पीछे देगा, तो MP को देख के नहीं DC शिफ्ट देंगे ताकि वो सेकंड वाला केस ना हो जहाँ पे कुछ पार्ट नीचे रह गया नेगेटिव साइड.
हाँ, MP को देख के देते हैं.
MP को हमेशा देख के उसमें
हाँ. You choose A such that कि वो ग्रेटर हो जाए फॉर ऑल टाइम्स टी, ठीक है? तो वो हम जब तक हमें MP का ही नहीं पता चलेगा तो किस तरह पता चलेगा कि भाई क्या हमने DC शिफ्ट देना, ठीक है? ओके, एफिशिएंसी का हमने फार्मूला जो पढ़ा है, इफ एनीवन तो ये हमने क्या निकाला, PS आता था 1/2 टाइम्स एवरेज पावर इन m स्क्वायर ऑफ t, ठीक है? प्लस 1/2 टाइम्स a स्क्वायर, ये हमने निकाला था, ठीक है? इस फार्मूला में सब्स्टिट्यूट करें इस फार्मूला में ये सब्स्टिट्यूट करें, एवरेज पावर ऑफ माय मैसेज सिग्नल क्या बनेगा? यस, बी स्क्वायर बाय 2। इसको आप सॉल्व करें, b की जगह म्यू a सब्स्टिट्यूट करें, ठीक है? ये यहाँ पे सब्स्टिट्यूट करें, यहाँ पे भी और यहाँ पे भी। एवरेज पावर ऑफ माय मैसेज सिग्नल, ये मैसेज सिग्नल था ना, इट्स अ साइनोसाइड, तो एम्पलीट्यूड स्क्वायर बाय 2। तो तब आपके पास क्या आ जाएगा? सब्स्टिट्यूट करने के बाद, कैंसिल करने के बाद, कॉमन लेने के बाद, ठीक है, एक्सप्रेशन क्या आएगी? करके आप बताना। यही आएगी, ठीक है? 1/2 कॉमन ले लिया तो ये बन जाएगा म्यू स्क्वायर बाय 2 प्लस म्यू स्क्वायर, ठीक है? टाइम 100%। ओके, नेक्स्ट स्टेप में आपने क्या करना है कि म्यू की डिफरेंट वैल्यूज गिवन है कि फॉर म्यू इक्वलेंट टू 1, फॉर म्यू इक्वलेंट टू 0, म्यू 0 तो एफिशिएंसी बिल्कुल आपकी पीक पे पहुंचेगी, फॉर म्यू इक्वलेंट टू सम प्रैक्टिकल वैल्यू 0.7, म्यू इक्वलेंट टू 0.3 एंड म्यू इक्वलेंट टू 1 फॉर द बेस्ट केस, ठीक है? म्यू इक्वलेंट टू 1 फॉर द बेस्ट केस। आपने एफिशिएंसीज निकालनी, ठीक है? तो ये क्या निकलेगा? सब्स्टिट्यूट द वैल्यूज, जस्ट सब्स्टिट्यूट में बताओ कितनी आती है? 0.7 के केस में एफिशिएंसी कितनी आती है? परसेंटेज में बी स्क्वायर तो ये 1/2 कॉमन ले लिया, इन अदर वर्ड्स यहाँ पे 2 आ जाएगा। हाँ, सही लिखा है, देखो ना, इसमें से आप 1/2 कॉमन ले लो, ऊपर से भी नीचे से भी, ठीक है? हाँ। 19 परसेंटेज, और ये कितनी आती है? 0.3, 33.33, राइट। तो यहाँ पे नोट करो कि ये बेस्ट केस था, ठीक है ना, म्यू इक्वलेंट टू 1 वाला। इस केस में भी जस्ट 33.3% आपकी efficiency है, power efficiency, ठीक है? Only 1/3 of the power approximately is being used for the sideband and for the actual data transmission. Rest is wasted. Normally we use this thing 0.7. ये practically use होती है 0.7. इसमें भी just less than 20% है, ठीक है ना, power efficiency. तो normally less than 20% है। तो ये तो entirely जो सिस्टम है आपका पावर इनएफिशिएंट सिस्टम है। अगर आपका पॉइंट टू पॉइंट कम्युनिकेशन होती तो डिज़ाइन प्रॉब्लम के केस में इन टर्म्स ऑफ पावर एफिशिएंसी आपका सिस्टम तो इनएफिशिएंट होता, हाईली इनएफिशिएंट सिस्टम, ठीक है? दैट्स वाई ये पॉइंट टू पॉइंट के लिए तो यूज़ ही नहीं होगा। However, one transmitter can afford such power inefficiency. So that's why broadcasting application suits well to this kind of scheme. ठीक है ना? तो that's why उसमें ये इसी तरह की चीज़ यूज़ होती है। Right? So I think you can link the concepts with the different types of modulation schemes कि भाई किस application में कौन सी यूज़ हो रही है। Broadcasting के लिए हम ये यूज़ करें and rest के लिए हम coherent यूज़ करेंगे। क्योंकि आपके रिसीवर्स बहुत कॉस्ट इफेक्टिव बन जाते हैं, ठीक है ना, यानी जस्ट इनवेलप डिटेक्टर्स आर रिक्वायर्ड, डायोड और कैपेसिटर रेजिस्टर का नेटवर्क है, यानी लेट मी शो यू द नेटवर्क जिसकी हम बात कर रहे हैं बार बार। अदरवाइज आपको फेज लॉक लूप्स वगैरह लगाने पड़ेंगे और कम्प्लेक्स सर्किटरी होगी, ट्रांसमीटर की तो नहीं, रिसीवर की कम्प्लेक्स सर्किटरी होगी। अच्छा, यहाँ पे मैं आपका बात काट रहा हूँ, सॉरी, मैं वापस आता हूँ। कहाँ गए? नेक्स्ट, ये दिस इज द टिपिकल डिटेक्टर फॉलोड बाय सम फिल्टर्स, ठीक है। इसके आगे सब फिल्टर भी लगे होते हैं, फिल्टर भी अगेन कैपेसिटर रेजिस्टर का नेटवर्क ही होगा, ठीक है। तो ये सिंपल सर्किटरी है जस्ट फॉर द डिटेक्शन। इसमें डीसी शिफ्टेड आपको यहाँ पे सिग्नल मिल रहा होगा, ये जो आप नोट करें, अगर इफ़ यू फॉलो द इनवेलप तो इट्स डीसी शिफ्टेड। आगे आप कैपेसिटर लगा ले तो ये रिकवर हो सकता है। तो ये बहुत सिंपल सा सर्किट है, इसमें जस्ट हाई स्विचिंग डायोड आपको चाहिए, ठीक है ना, और कुछ नहीं चाहिए, ठीक है। बाकी आरसी कांस्टेंट तो आप डिफरेंट कैपेसिटर और रेजिस्टर के कॉम्बिनेशन से चूज कर सकते हैं, ठीक है ना। वी विल सी इन द नेक्स्ट लेक्चर कि ये जो आरसी कांस्टेंट है, जो डिस्चार्जिंग का जो टाइम है कांस्टेंट है, ये क्या होना चाहिए, किस रेंज में होना चाहिए, ये हम डिस्कस कर लेंगे फॉर्मली इन द नेक्स्ट लेक्चर। नेक्स्ट लेक्चर में हम एक दो और सर्किट्स भी देखेंगे। डीमॉड्यूलेशन के डिफरेंट सर्किट्स हैं, जनरेशन के डिफरेंट सर्किट्स हैं जो आपकी बुक में भी मेंशन है, different ways of generating the amplitude modulation, synchronous as well as non-synchronous.